In order to understand a lot of addition reactions to alkenes, we have to understand the stability of carbocations and where that stability comes from. And the reason for this is simple, because a carbocation is the key intermediate for most of these addition reactions, okay? So we have already seen carbocations, and we see that the more stable carbocation is formed the fastest, and it also dictates the product formation. So because of that, we have to know how to, when a reaction occurs, where is the most stable carbocation going to be? Why is it more stable? And what um, what do substituents that are around that carbocation do to its stability? So what do we know so far? Well, we've simply looked at simple carbocation situations where we see that tertiary carbocations are more stable than secondary carbocations, and secondary carbocations are more stable than primary carbocations, and primary carbocations are more stable than the methyl carbocation. But we've never really explored why. I've simply told you this is the way it is, and um, we've never gone into detail other than saying that alkyl groups donate electron density. But we have to think about why, and when we do, then we can really start to understand a lot of the intricate and detail of the chemistry that's going on in when we have the formation of carbocations. So there are mainly two effects that dictate carbocation stability. One is called an inductive effect, and the other is what is referred to as hyperconjugation. Hyperconjugation. So let's explore the inductive effect first. Right? Inductive effect simply means that you're moving electron density through a sigma bond. That is certainly the characteristic of what we term inductive effect. So if I look at a carbocation, I see that carbocations are sp2 hybridized. Now, what does this mean? Well, it means that we've increased the S character of that carbon, and hence we increase the electronegativity of that carbon. So when I think about a carbocation, here I have a methyl carbocation, and of course that carbon, relative to an sp3 carbon, I've increased the electronegativity of that carbon, and so it's going to try to withdraw as much electron density from sigma bonds as it possibly can. And of course, it's going to withdraw electron density away from the hydrogens, but hydrogen doesn't have much electron density to begin with. And therefore, this is a very weak dipole moment simply due to the fact that hydrogen doesn't have electron density. Now, when I put other substituents around that carbon, like sp3 carbons that are less electronegative than an sp2 carbon, then I can see that I donate electron density to that carbon through the sigma bond, and I can stabilize it. So sp3 carbons can donate electron density through a sigma bond. Now that is one effect, and certainly it is a legitimate effect. But the second effect is even more important, and that is hyperconjugation. Hyperconjugation, not higher conjugation. So hyperconjugation. Now, what does hyperconjugation mean? Well, if I take a look at here's my carbocation, and I'm of course looking at a tertiary carbocation, so I have three methyl groups, and I'm going to highlight, now notice I haven't drawn the hydrogens on one of those methyl groups because I'm going to highlight those bonds there. And if we think about what's going on in this molecule through a sigma bond, I have free rotation, and at one point in that rotation I have an eclipsed conformation of the carbon-hydrogen bond with the empty p orbital of my carbocation. Now, generally speaking, we think of eclipsed as being less stable. But in this situation, what do I have? I have an empty orbital. The reason why eclipsed conformations generally are less stable is because of electron repulsions that are occurring. In this scenario, I have an empty p orbital. And if I think about that sp3 or the sigma bond between carbon and hydrogen, that sigma bond is aligned with that p orbital. Since there is overlap that can occur of a filled orbital of the carbon-hydrogen sigma bond to the empty orbital, p orbital of my carbocation, I know this is going to produce stabilization. Why? Because overlap of any empty orbital with a filled orbital stabilizes species. So here we have the overlap of the empty p orbital with a filled sp3 orbital, and so it helps to stabilize the carbocation. We can envision this in terms of molecular orbital theory by thinking about this empty p orbital and how it's going to mix with the sigma bond carbon-hydrogen bond, right? It is filled, and therefore they're going to mix to produce two new orbitals, one lower in energy, one higher in energy, and of course, since I only have 2 electrons in here because the p orbital is empty, then I produce a net stabilization. That is what we call hyperconjugation. It's almost, it comes from the conjugation, right? That the two carbons are conjugating to one another. Now, I want you to think about this for a second because we have discussed rearrangement, carbocation rearrangement. So think about what happens in a carbocation rearrangement. Of course, I'm going to explore this in more detail later on. Carbocation rearrangement happens so much, it's basically from this hyperconjugation where I'm donating electron density so much that I actually produce a more stable carbocation on the carbon that initially has that sigma bond. So we'll take a look at that a little bit later on. Now, why can't a methyl carbocation do this? Well, if you look at the methyl carbocation, you see that there is no orbitals that can overlap. It pays close attention to the orbitals that are overlapping. There's no, the carbon-hydrogen bond is not overlapping. It's an adjacent bond that is overlapping. And so when you just have hydrogens, there are no other orbitals present that can donate electron density to that empty p orbital, right? So that is hyperconjugation. And that is the main reason why alkyl groups, which can produce hyperconjugation, stabilize carbocations. Now, there are other factors that can influence carbocation stability, and that is substituents that are present, that are close to that carbocation. So we also see that substituents can affect carbocation stability. How? Well, again, through inductive effect and or through resonance effect. So we're going to see that substituents can have an inductive effect one way and a resonance effect another way, and how do they balance one another out? So let's take an example of where I have a pi bond here, and the pi bond is undergoing an addition reaction to HBr. All right, so on an adjacent carbon, so this would be an allylic position, right? Because that CH2 is an allylic carbon, and so let's say I have some substituent on that allylic carbon, and we don't know what that substituent is, and so we're going to assume that HBr is going to add, and because that carbon has both inductive effect and hyperconjugation, that allylic carbon is going to stabilize somehow the carbocation, and we're going to get this carbocation. So hydrogen goes to the carbon on the right, and the carbon on the left becomes a carbocation. Now, what happens to the rate of this reaction when we vary X? Well, let's say X is either a hydrogen or a halogen. So hydrogen is kind of our baseline, and now bromine is certainly electron withdrawing, right? And we look at the rate of this type of reaction, and we see that for hydrogen it's 1, and so that's a relative rate. We're setting um, basically propene, the rate of addition of propene to 1. And now when I take 3-bromopropene and I compare its rate to the rate of propene, I see that it's drastically lower, so 10 to the minus fourth times less or slower than that of propene. Why? Well, if I look at that structure where X is bromine, and I think about the intermediate carbocation, I know that bromine withdraws electron density away from um, that allylic carbon, right? Through inductive effect, it's withdrawing electron density. And what happens is it places a negative charge on the bromine, obviously, partial negative charge on the bromine, and a partial positive charge on the carbon. So here I have the allylic carbon that has a partial positive charge, and my carbocation that has a formal positive charge. Obviously, this is a bad interaction, right? And therefore, it slows the rate of addition down drastically. Now, is that the only effect that can happen? Well, certainly in this scenario, the only thing that bromine can do is inductively um, um, affect this carbocation stability. And so inductively, it's withdrawing electron density because it is more electronegative than that carbon is. However, let's look at a different situation in which a halogen is connected to the alkene carbon. So this is called vinyl chloride because the chlorine is connected to a vinyl carbon. Now, when I react vinyl chloride with HCl, I could get one of two products. So I could get the hydrogen adding to the carbon on the right and the chlorine adding to the carbon on the left, or vice versa. And notice they would be different products. This is the product that I get. So I end up getting 1,1-dichloroethane. I do not, I repeat, I do not get 1,2-dichloroethane. And if you think about the reason for this, again, we have to think about carbocation stability. So let's draw vinyl chloride again and think about the mechanism of the carbocation forming, right? The pi bond is going to interact with the sigma star of HCl, again, reinforcing what's happening at the HOMO of the pi electrons in the HOMO are reacting with the sigma star LUMO electrons of HCl, producing, it has to be this carbocation that I'm showing. Because the hydrogen we see is going on the carbon on the right hand side. So you might say, well, the chlorine, doesn't it withdraw electron density? It certainly inductively withdraws electron density. It is more electronegative than the carbon. And you might be thinking, well, that is a destabilization effect. But remember, there's always two possible effects. There's inductive effect and there's resonance effect. And it's important to understand that that chlorine has 3 non-bonding pairs of electrons. And those non-bonding pairs of electrons can donate electron density, like so, to that carbocation, right? So just like we see in hyperconjugation, where you have a sigma bond donating electron density to stabilize, in this case, we have non-bonding pairs of electrons that can donate, and we can actually draw a new resonance structure which shows that there is some pi character between carbon and chlorine, and now the chlorine has a positive charge. Now, obviously, between these two, which one is going to be the favored Lewis structure? Well, in the structure on the right-hand side, we see that all atoms have an octet of electrons, right? And the structure on the left-hand side, carbon, doesn't have an octet of electrons. And so this is certainly going to be resonance stabilized, okay? Obviously, if a nucleophile attacks, it's going to attack the carbon. It's not going to attack the chlorine. Because if a nucleophile attacks, well, the chlorine can't accept any more electrons, right? And carbon would then have an anion. Electrons would go to that anion. So nucleophiles still are going to attack that carbon. But the key is to understand that that chlorine, when it's attached to the carbon, has both inductive effect and resonance effect. Inductively, it certainly is going to withdraw electron density, but through resonance, it can stabilize it. And whenever you have a delocalization of electrons through resonance, that produces a high stabilization. So the key is to understand that whenever possible, resonance effects overcome inductive effects. That is the key. Whenever you don't have resonance effects, you have to think about the inductive effect. But when you do have a resonance effect, the possibility of drawing a resonance structure, you better think about that, okay? Now, I say resonance effect dominates, and as a matter of fact, it can even affect product formation, the types of products that you get. What do I mean by that? Well, let's look at an example where I have 1,3-butadiene reacting with HBr. Now, you're going to explore this reaction in a lot of detail later on, but I just want to highlight to you what can happen based on resonance stabilization. So here we have essentially 2 pi electrons that can attack HBr. So both sides can attack the HBr. And I'm going to assume that the side on the right closest to HBr is going to attack, right? Now, what happens when the pi bond attacks HBr? Again, I generate a carbocation and then bromide attacks. So I would expect to see this product, right? I've added HBr across the double bond. But what I actually find is I certainly get this product, but it's actually the well, depending on the temperature, it can be the major product or the minor product. The other product is this, right? So what's going on here? Well, at first glance, we see that if we numbered the 1,3-butadiene 1, 2, 3, 4, in the first product, we see that H and Br have added to the 1 carbon and to the 2 carbon. And this is called 1,2 addition. In the second product, we see that the hydrogen actually has added to the 1 carbon, but the bromine has added to the 4 carbon, and this is called 1,4 addition. 1,4 addition. Now, obviously, the pi bond also has migrated somehow. And what's going on in this process? In order to understand that, again, we have to think about the mechanism of the reaction and the carbocation that is formed in the process. So let's think about that. Here we have 1,3-butadiene reacting with HBr. The pi bond attacks the sigma star of HBr, and I'm going to form a carbocation. Now this carbocation is a special type of carbocation. It is an allylic carbocation because adjacent to that carbocation I have a pi bond, and that pi bond I can use to stabilize through resonance. I can move those electrons to that carbocation and I produce a new carbocation. So this is something that we talked about at the very beginning of the semester, and if you need to, certainly review resonance forms because this becomes very important in understanding carbocation stability and carbocation what we call migration, right? So these two species are resonance forms of the allylic carbocation. And we have to understand that both of those forms actually really don't exist in their true form. But what we have is a combination of the two that places a positive charge on essentially the carbons on the end, but no charge on the carbon in the middle, which is why we never get a nucleophile adding to that particular carbon. And so we can simply look at the two resonance structures of that allylic carbocation. And in the first one, if bromide adds, we're going to get what we call that 1,2 addition. And then in the second one, if bromide adds to that carbocation, we get 1,4 addition. The other thing that I want you to notice is that in that second allylic, that second resonance structure, it it looks like we have a primary carbocation. And I've been stressing to you for weeks now that primary carbocations don't form. But remember, this is not a primary carbocation. It is an allylic carbocation. And because of that, we have, a general delocalization of positive charge, which does place a slight positive charge on that particular carbon. So there are a variety of substituents that can affect carbocation stability in both a positive way and a negative way. And we have to be cautious about when we form a carbocation, what does the structure of the resulting carbocation look like? And are there any possible inductive effects that are going to destabilize or stabilize for that matter? And are there any resonance effects that can distribute that carbocation charge throughout to stabilize and or possibly promote rearrangements, which is what we're going to look at in just a little bit.